welcome to the week 3 of the problem solving session. Okay, so yeah, I think one major algorithm that was discussed in this week was the finding local minima. In okay, one thing that we did was in a 1D array, and the second one was in a two-dimensional array, which is a grid. Okay, so for the one-dimensional array, what was the best bound that we saw? So uh, what is the time required to find a local minimum in a one-dimensional array? So you have an array A and you want to find an element such that its neighbors are larger than it, both of its neighbors. So one way of doing that would be scan through the entire array, so and find minimum element. So that will be an order and time algorithm, right? So find a of I such that a of I minus 1 is less than ai, and sorry, a of I is smaller than a of I minus 1 and a of I plus 1. This is what we want to find out. So one way would be that you scan through the entire array and find the minimum element. That's your order and time algorithm, but can we do better? Yeah, anyone? Okay, so I'm assuming that you have all seen this in the lectures, that you can actually improve this to order log n, correct? Is this fine with everyone? And which was the idea was basically similar to binary search, and um the idea is that you keep your left pointer here and the right pointer here, and you find mid here. So mid will be L plus R by 2. Now you go to the mid and check whether this mid is actually a local minimum. If it is, then you output that. If not, then it could so happen that either this or this is smaller. Okay, so let's say this is the minimum, then you update your um, pointers accordingly. So if this is the minimum, then you update your right pointer, and if this were the minimum, then you update your left pointer and divide your search space into half, and you repeat this. This is a recursive procedure, so at the end you're guaranteed to find a local minimum. Note that we're not finding a global minimum, so finding a global minimum must take omega n time, but because we're only looking at a small neighborhood, we can do an improvement. Okay, um, so what about 2D grid? So how did we define that? Finding a local minimum in a 2D grid is that, let's say this is an n cross n grid. Okay, then I'll say that this element is minimum if uh, if the adjacent cells all have a value larger than this element. Okay, then I'll say that this is a minimum. We're not looking at the global minimum here. Okay, so a trivial way of doing this again would be that you go through all the cells, scan the entire matrix, and find one minimum uh, element. And because that is minimum element, everything neighboring to it will also be smaller. So then you can output that. But that would take a trivial scan algorithm would be scan through entire grid and find the minimum. So this will take order n square time. So can you do better? Have you seen better algorithms in class? I mean, if you know the answer, please feel free to unmute and speak, or use the chat, or uh, yeah. I mean, I'm assuming that you have seen the lectures. Is that correct? Okay. The question is, you have this n by n grid, and you want to find a local minimum, which is an element whose adjacent four cells have a larger value than its value. So trivial algorithm would be, you go through the entire matrix, scan it, find minimum. That is your order n square algorithm. But can I do better? So what is the best algorithm that you know of? I hope the question is clear. Is the question clear now? Okay. So, so if you have, in case you have not checked out, please look into the lectures. I'm not sure if we'll be able to cover this thing, but yeah, the first improvement that you saw was from n square to n log n, and in the next step, you actually showed that you can do even better. You actually do an order in time algorithm, which is basically a divide and conquer strategy. So actually, both of these ideas are divide and conquer strategies, but this is more. Uh, this is a stronger. Uh, um, so you start with a stronger hypothesis, and yeah, and prove your invariant, and you end up getting an order in time algorithm. Okay, so okay, so maybe if whenever we look into questions about this, if something is not clear, then please raise the question. Okay. So yeah. So another problem of similar flavor that you saw was finding um, maximum sum subarray in an array. So given A, you are given an array A, and um, it contains this is an array A of n elements, and these are all integers, so of n integers, let me just say. Okay, so you want to find, given this array A, you want to find sub array B which is sitting inside it, such that if you sum the elements, sum of the values of all the elements in B, that's going to give you maximum sum among all possible subsets. So there are 2 to the n possible subsets. So your trivial algorithm was that you go through all possible subsets, find out the maximum, and output that value. So this was your exponential time algorithm, but you actually saw that you can bring it down to linear. So this, you ended up giving an order and time algorithm, which was that you maintain your maximum sum till previous point, like, and use that information to find the new maximum. So you sort of do this in a few scans. That was your idea. So let us say that you are extending this problem to a grid now. Okay, so instead of an array you have a grid. So this is your n by n grid, and okay, this is the input that's given to you. I'll call it G. So this is the grid G that's given to you. It consists of distinct integers. So each cell contains distinct integers. Now, what is the natural question to ask here? Here you asked for a subarray whose sum is maximum. Natural generalization of this problem would be, I'll ask you for a subgrid or a submatrix such that if I sum up the values of all those elements in the grid, then I get the maximum sum. So this is the input that's given to you, and output a grid G prime sitting inside G such that summation of um, all the elements of G prime I, so this S is larger than summation of um, H of I for any grid subgrid H of G. And when I say subgrid, I basically just mean that you're going to select two rows, okay, and you're going to select two columns, and whatever is in the intersection, that is your subgrid. Okay, so what is a, is the question clear, or shall I repeat the question?
It's clear, ma'am.
Okay, thanks. So, what is a trivial algorithm? Let's say, let's not even worry about fast algorithm. What is a trivial algorithm to find this maximum sum?
Is factorial n or n to the power of n?
Okay, so what is the idea? So, how many total grids can be there? How many subgrids can be there inside G? So, a subgrid is
Yes.
the. Huh.
Oh,
Okay, so a subgrid is defined by choosing two columns ij and two rows, let's say kl, and whatever is in the intersection of that. So um, g of all x comma y such that x is between I and j, sorry, x is between k and l, and y is between I and j. Okay, so this is the mathematical, I mean, this is how you'll mathematically write it. So all the elements g x comma y such that x is between sorry, x is between these two rows and y is between these two columns. So whatever is the intersection will give you the grid. So how many choices are there, for how many total possible grids are there? You have um, you have n choices for, you have n choices for I, you have n choices for j. Similarly for k and l, you have n choices, because The number of rows and the number of columns is n. So how many total choices do we have for selecting grid?
This is n square, ma'am?
Yeah, so you have n here and you have 4 possible choices, right? So n to the 4.
Yes, ma'am. N to the power of 4.
Yeah, so you have n choices for I, j, k and l each. So altogether you have, which is n to the 4 possible grids. Now, now once you have a grid, you're going to sum up all the entries inside it. Okay, so how much time can that take in the worst case? You have n square elements here, right? It's an n cross n matrix. You have order n square elements. Let's upper bound it. Each grid has order n square elements. So finding sum of subgrid G prime will take, let's say, order n square time. Okay, so there are n to the 4 possible grids. Every, let me not call it G prime, I'll just call it H. Okay, so and every subgrid is going to take order n square time to find the sum. So altogether, how much time is this?
N to the power of 6, ma'am?
Yes, yes. So you have order n to the power 6 time, and you basically want to find maximum sum. So what you will do is every time you encounter a sum which is larger than your previous one, you will update that. So this doesn't take. I mean, you can save space in such a way. Just keep the current maximum, and at the end of your iterations, just output whatever maximum you found. So this should take you order n to the 6 amount of time. So
Okay.
this is the brute force algorithm where we did not try to optimize anything.
Yes.
Yeah. So um, suppose you want to improve this. Let's say we are not happy with n to the 6 and want to bring it down. So um, what sort of ideas can you think of?
Is divide and rule horizontally and vertically separate.
Okay. So what is the I mean, what does the algorithm do? So when do you decide to divide? Okay, so one hint is that think about what you did in the 1D case when you only had, uh, you did not have this matrix or grid, but you only had this one subarray.
Okay.
Okay, so what did you do? You kept for every element I, you had this S of I, which stores maximum sum of subarray that ends at I. And using this value, you found out S of I plus 1. Using S of I plus 1, you found S of I plus 2, and so on, all the way,
Okay.
iteratively. Correct.
Yes, ma'am.
Okay. So, so let us ask a simpler question now. So, the point is that you have to make four choices, right? You have to decide this call sorry yeah, you have to decide two columns and you have to decide two rows and then look at the
Rules.
grid. So
Yes.
let us simplify the question. Let us say that columns are decided, so forget about um yeah, so let me draw this again. So let us say that I give you, okay, this was your original grid, and I'm cutting off this portion of matrix. Okay, I'm telling you that this is your column, these are your two columns. Now how many subgrids are possible? um, there are n square possible subgrids because there are choices of two rows that you need to make. This k can start somewhere of I mean could be a choice of yours, and this l could also be a choice of yours. So depending on choices of k and l, you are going to have now n square possible subgrids. I'll just call them grids if columns are fixed. Okay, so can you do uh, something here instead of doing the naive approach of going through all possible subgrids here? Can you think of something better, and focus on the fact that your columns are fixed? That means you cannot do something like this. You cannot say now that this is my subgrid. You have to take whatever is on the, you cannot choose to not take the borders. You will have to take elements along these lines, some subset of elements along these lines and some subset of elements along these lines. You cannot violate the border. So does that yes, so yes, you have to modify the um, cadence algorithm. So how will you do that? um, Good, yeah.
And we will fix the left column and the right column and then
Yeah, columns, I mean, you don't have a choice of columns now, so columns are fixed, but you have to choose which rows, which subset of row and which choice of rows will give you maximum sum. So how will you find that?
ma'am, it was the we can add the elements between these two column row wise, and this converts the 2D array into 1D array, and then we will apply this Cadam's algorithm.
Yeah, so yeah, that's correct. So the point is that, notice that if I say that um okay, if I have to take the row 1, then I have to take all of the row 1. Okay, so all these entries will contribute towards the sum. So if a row r is participating in the grid, then all its entries contribute to the sum. Okay, and in particular, if I choose rk and rl to be the rows, then sum of grid um, defined by um, I j k l. Let me just write it like this. Basically, I mean to say the grid between ij columns and kl rows. This sum is nothing but summation of entries of the rows. um, yeah, yeah, So SI denotes sum of um, yeah um, elements in G um, in row I and corresponding to columns. um, okay, sorry, I is a bad notation, I is overused, so let me call this M, row M and corresponding to columns I and J. Okay, so basically sum of entries in this particular grid is nothing but sum of entries in this row plus sum of entries in this row and so on all the way up to here. That's what we are saying. So okay, and another point is that if you decide to choose one particular row, you have to take all the elements in that row because your boundaries are now fixed. So so the choice really is you can think of this as so you can think of this array S of k to S of or let's say S1 to Sn. So S1 denotes the sum of all the entries in the first row between I and J and so on, right? So you're going to sum up all these row elements between these two columns and you'll write it here. Okay. And now the question really is what subarray here maximizes your sum? Because yeah, because let's say this is the subarray that I choose that basically gives you the grid, right? Because each element here is this part. So is this fine?
Yes, ma'am. Yes.
Okay. So what is the time complexity of finding this um
Order of n square.
mm, no finding the finding the selectors k and l that will maximize your sum. So you use the same algorithm, right? You'll use uh, cadence algorithm and you will find this in order in time, right? Okay, so
Ma'am, order of n is it?
yeah,
And space complexity is order of 1, I think.
uh, well, you are storing these values, right? So you have to store s1 to sn, like you don't have a, I mean, so you'll need space for that. So there's at least n amount of auxiliary space that we're using.
Can you able to brief cadence rule, ma'am?
Yeah, sure. Yeah, so the idea was that okay, maybe I can just go back to the yeah. Yeah, so this was our um, algorithm that we said that S of I stores the maximum sum of subarray ending at that point. And in order to find this efficiently, you said that let's say I have s of I minus 1 that is available to us. So the maximum ending at I can subarray ending at I can either be that you look at the maximum until now, that is s of I minus 1, and add the new element a of I to it. So s of I is maximum till now with the new element. Or it could be that maybe this sum, previous sum was negative, so I don't add it because that will only reduce my total sum. So I'll discard that previous element, previous sum, and only take a of I. So for example, here if uh, s of, let's say, um, this is the array that's given to us, then maximum sum uh, that you can get for an array ending at this point is, you don't have any choice, you have to take this element. So at this point you have minus 2. And then let's look at 1. You have two choices here. You can either take this subarray or you can take this subarray. If you take this, then your sum is 3. If you take this, then your sum is 5. So therefore in that case you won't be taking this, but you will just be taking a of I. But in the next step, as you can see, you if you take this sum, then you get your maximum. So sometimes you may have to take previous sum and add to it, or you may have to discard and just take the current sum. So this entire step can be done in one scan. So that's where you had your order in.
Thank you, ma'am. Thank you. Thank you.
Sure. So that's the idea. And yes, there will be some time that we spend into finding these sums. Okay, so let me say that I'll compute it at one stretch, and let's say I spend some order and square time in doing that. And now I have my sums ready, and then I apply this algorithm. So for a fixed I and for a fixed j, you can find maximum sum grid in order and time. So suppose I spend order and square time in pre-processing. That is, I keep the sum ready. Okay, and now what we will do is for fixed columns I comma j, you can find maximum sum grid between I and j columns in order and time. So now what is the natural thing to do? Now you will go across all possible ij. So there are n choices for I, there are n choices for j. So go through for each I in 0 to n minus 1, for each j in 0 to n minus 1, find maximum sum grid between columns I and j, and let us say that g prime is the maximum that you get. Then you will update max to g prime, and you can initialize max to minus infinity, let's say. Okay, and at the end of these two loops you will output max. So that's your algorithm. So what is the time for this? You have one loop here that runs for n steps, one loop that runs for another n steps, and this is an order n time operation. So altogether this is an order n
Ma'am,
time.
what is the time complexity for this? Sorry, space complexity.
Yeah. Yeah. So right now if I use more space, what I can do is in in one scan itself I will keep all these sums ready with me. So how much time will that how much space does that take? That should be Hmm. Okay, actually you can do something better. You can, so let's say that these are the two columns that these are the columns that I was looking at, and I decide to increase my I to I plus 1. I just need to add one more entries to all of them. So this can be updated in order and time. So if I keep this entire so I mean matrix ready with me, this space will be roughly n square, because for every choice of I and j there is one matrix that I'm keeping ready. Okay, but if you want to save on space, then you might end up spending a little more time. I'm not sure, but yeah. So for now, I'm not worrying about space. So you will get um, roughly n cube time algorithm. So um, is this okay, or are there any questions?
Still, any more time can be reduced, man?
Hmm. Okay, that is a good question. Uh, hmm. I think n square is something that you may require. So n square should be a lower bound, because um, your entire matrix itself could be the biggest matrix, right? The matrix that achieves maximum sum, right? So for example, all the entries are positive, there are no negative entries, then what is the maximum sum? That you take the entire matrix. So that means you have to look at every entry at least once. So lower bound trivially should be omega n square, because you need to look at every element. Okay, so there is a gap between these two. I'm not sure if you can do better, um, but yeah, there is a possibility. Okay.
Thank you, ma'am. It's really good.
Okay, any other questions?
Can you explain why, in a scenario where average cases can be used?
Sorry, can you repeat the question?
Uh, can you explain? Do we have any scenario where average cases can be used? Average case,
Average case can be uh,
yeah, used.
used. Average case as in average case input, or you mean average case time analysis?
Average time complexity.
Okay. So one yeah, one place is, I mean, so this order notation is good in theory only to, I mean, to give theoretical bound, but in practice, um, I mean, let's say, I mean, suppose let's talk about sorting algorithms, and you know that um, for example, you know that the inputs that are coming to you are almost sorted all the time. So so if you use quick sort or merge sort or something, you will um, you will end up using n log n time, and in according to the theoretical analysis, your selection sort or insertion sort that would give you n square. But you know that your input has this property that it is almost sorted, right? So you may not have to do a lot of shuffling to make the new array sorted. So you're only spending like order and time every time. Okay, there may be some cases where the input is bad, then you have to spend a little more time, but so let's say uh, let's say I1 to in, these are the inputs that keep coming to you, but I give you a guarantee that 3/4 of them are almost sorted. So 3/4 of times you are spending order and time, and 1/4 of times you are spending like n square. And okay, and n is not too large for us in practice, and may not be, and we don't work with arrays of millions or billions of size normally, right? So when you sum up this, on average you are saving time by using insertion sort. So there is something called um, amortized analysis that we use. We don't sometimes use the worst case um, complexity because it doesn't capture the um, I mean the complexity of the problem entirely, because it depends on what kinds of inputs are coming to you. So there is this entire area where you do such sorts of analysis. But yeah, that is just one kind of analysis for yeah, I mean when your input satisfies certain properties. Okay. Hmm. So um, okay. So this question is related to the local minimum question. This is not related to the maximum sum subarray. So your local minimum was that, yeah, find an element I such that its neighbors have larger value than itself. That was your problem. And you use the binary search sort of strategy, right? Whichever is the minimum neighbor, you move towards that half and keep on having. So and in that algorithm we assumed that um, all the elements are distinct. So suppose that's not the case, okay, and you end up using the same algorithm, will you still be doing an order login? Uh, I mean, you'll still have an order login algorithm, or is something wrong? Um, so what does the intuition say? Should it work? Because I mean, we're not really making much of a change. We're only allowing, I mean, the only condition we changed is that instead of saying that they are distinct, we are saying that they're not distinct anymore. Neighbors may be the same. So something like, so this could be.
So it can't be order log n, ma'am.
Hmm. Mm, yeah. Where does it fail? So can you come up with a counter example where if we apply the same algorithm, we will end up failing. We will not have a correct answer.
Positions of the same numbers are same, ma'am, or either it will be changed, ma'am? It can be changed.
Positions of
Same
repeated.
element, I mean,
Ha,
a
so
repeated element.
yeah. So let's assume that only the neighbors can be the same. So for example, 4, let's say this element is 4, its neighbors can be 4, but then you cannot have a 4 here. Let's assume, like, if you have repeats, you will have a block of repeats, but you cannot
Okay.
have, yeah, here. So let's try to apply the algorithm here itself. Let's say this is the array, and this is your left, this is your right.
Okay.
So what is the mid? Okay, let me slightly modify this array. Okay, so right now there are, okay, let's just remove one element, that's it. Okay, so what is the mid here? Mid is so mid is the fourth element, the uh, index at 3. Okay, and now what does the algorithm say? So what does it say? You look at mid minus 1, a of mid minus 1, and a of mid plus 1.
Bit plus 1.
Yeah, and whichever is minimum, you go there, right? So you
Okay.
move to that half. Okay, but now the problem that arises is that there are duplicates here. So I don't know, I mean, they are the same, right? So we can't make a decision whether to go to the left or whether to go to the right. Okay,
Right. Yes, ma'am.
so if we arbitrarily decide, okay, let's say that I'll go to the right, then what happens is, then we are saying that our answer lies here, but that's not okay, sorry, we're looking for a local minima, right? So this example is slightly worse. Okay, what I should have done is, yeah, this is just, let's say, increasing. Yeah, now you won't be able to find a local minima. Yeah, in this subarray.
Then again, it will shift it to left.
But then you are not doing order login, because you are checking here as well, and then you are checking here
Yeah.
as well,
Yes, yes, yes.
and we don't know where it lies because this information does not reveal anything. So this would fail. So yeah, so the binary search algorithm fails because we cannot make a decision of having correctly. If we move to incorrect half, we may not find a local minima. So that's yeah. So there's just one slight modification um, to the algorithm that you had, where
Yes, ma'am. Yeah, actually, even for incorrect half you said, right? So
mm-hmm.
even if it is sorted, it won't work. I'm asking if it is
Yeah, yeah, yeah,
it won't.
yeah. Sorted with duplicates.
Okay.
Yeah. Okay. Any other?
What would be the time complexity, ma'am?
Yeah. So here it seems to me that you will end up doing order n, because um, I mean intuitively it looks like looking locally does not tell you anything. So it looks like you will end up scanning entirely. I don't know how to prove it. I mean, prove that omega n is the lower bound, but I think that should be the case.
Yes, ma'am.
Okay. Okay. So here
Ma'am,
is
ma'am, what is the best way to find the first and the last occurrence of the element using the binary search?
first and the
If
last occurrence in this case. You mean when
when
the
arrays of n size like
okay, so you just have an array of size n, and uh, um, you don't have any additional constraints that they are distinct or something that's not there.
yes,
Okay, so okay, so I mean, if you don't have any additional information about the array, then you will have to scan through all of it, because
if they are distinct, then
okay, if they're distinct, then yeah, and it's not sorted, even then it's order n, because no matter what algorithm you come up with, I can always give you an input where your algorithm will perform bad. So right, let's say your algorithm tries to um, um, move in a certain make search in a certain part. My adversarial argument will be I'll keep it on the other half, and then whatever you do, I'll create an instance such that you will have to scan through all of it, all of the array, for finding that element. um, yeah, so this is a known bound, by the way. If you have an array and you do not have any constraints, no additional information, then finding an element would take omega n steps. Okay. Does that answer your question?
ma'am, if array is sorted in the indistinct elements, find that array element of a of I such that a of I is equals to I.
Okay, so you have a sorted array A with duplicates, right? Repetition is allowed. Find I such that A of I is equal to I. Okay. Um, so can you modify the Okay. So if you look at, okay, I'm just trying to uh, apply the binary search algorithm as it is for now. You look at the mid, check if A of mid is equal to mid. Okay. If if yes, then you have found your answer. If no, then either A of mid is smaller than mid or A of mid is larger than mid. Okay, so hmm, okay, so suppose mid is 3 and the value is 5. um, then because your array is sorted, okay, hmm, hmm. Okay, so again you don't know where to go, right? Because your answer could potentially be here or it could also be here. Hmm. Hmm. Okay. Is there is there anything you can do better than order, and is that known?
No, ma'am, n is not known.
And I mean order and you can always do, right? Because you just scan through the entire array and check whether there is an I such that A of I is equal to I. So you mean lower bound is not known, or what? So I mean, like brute force would be scan through the entire array. That will give you order in time. But yeah, I agree that binary search does not work. Yeah, so I don't know if you can do better than order in. But if someone has any ideas, then feel free to share.
With the help of divide and divide and conquer problem, like are we able to solve in that way?
Yeah, so that is what I was trying to do. So we natural thing would be you take your left and right pointers here, go to the middle element, check if this condition is true. If it is true, then you are done, you have found it. But if not, then these two cases arise. And let's say that we are okay, sorry, I'm in this case, the value here is larger than the index. So that does not mean that I cannot have something like, sorry, that does not mean that something like this cannot exist, right? That can still happen. And also this is also a possibility that there is an element on the right half which actually achieves this. It could also be that there is an element on the left half which achieves this. So I don't know where to go.
So in binary search, is it applicable or we cannot apply this binary search
Yeah,
to
so
this way?
binary search is cannot, as it is, it does not work here, right?
Even if it's sorted or unsorted, both the cases.
Yeah, both the cases. When duplicates are allowed, yeah. Please.
Ma'am, if we are searching for a plus b is greater than 1000, so does it make sense that we should move only for the right side? Because the if the element is sorted and the condition is a plus b should be greater than 1000,
What is
then we
A
have
and
to move only for the right side so that the sum of two elements should be greater than 1000. You know, it's
what
better
is
to move.
A and what is B?
The
As
two
in,
elements of that array, sorted array. If the condition is a plus b is greater than 1000, in that case,
A and B are your indices, is it?
a and b are the elements of the array.
Okay, so what is the problem? What is the question that we are asking?
If the array is sorted and it has the n number of elements, and the two elements of the array whose sum is greater than 1000, so by finding that,
So
we
that's
should move only the right side of the array. Like if we have find it the mid, so we should move only right side to get the sum of two elements is greater than 1000. So we do not have need to move to the left side
but
The
I
because
prob-
the
thought that
element because the
problem is about local minima, isn't it, ma'am?
I
It's
think
not the
hmm,
problem is about the local minima. That is the problem actually.
hmm.
For unsorted or sorted, that the order will be ON only.
Yeah. So if you are talking about finding, yeah, a of I is equal, if that is the problem you are sticking to, then yeah, then we encounter a similar problem, as finding local minima. That this checking at mid is not helping us. It's not giving us anything. But this a plus b greater than 1000 thing, is that a different problem that you're talking about, or is it the same?
yes, ma'am, it's different.
Huh.
Ah,
Okay.
problem is different.
Okay. Yeah, so what is the point you're trying to make? So you want to find two elements A and B such that, um, or let's say I and J, such that A of I plus A of J is greater than 1000. That's your problem?
Yes.
Hmm. Okay, so trivial thing would be order n square. You want to do order n.
Ma'am, it's n elements now. So we have to find the two elements of the array so that the sum is greater than 1000. So we
Yeah,
have to
so
find the two elements of the
yeah,
array.
yeah. So your array is sorted. I'm saying the trivial algorithm would be that you go through all choices of,
And why we go all through? If we are able to find the mid and it's a binary search, we should move to the right side now because the uh, greater elements will be only on the right hand side, not in the left side because the array is sorted, isn't it?
yeah, I'm just doing a step by step process. I'm just uh, writing the first bound that you can get and then do a better algorithm, right? So trivial algorithm gives you order n square times. So how do we do better? Yeah.
Yes.
Okay, so you're saying use the binary search idea. Hmm. Okay, so you look at mid. Okay, and if your mid is greater than, mm, hmm, yeah, if your mid is greater than 500, then there is something which is of value at least 500, so you have a subarray whose sum is larger. In that case, you're done. Otherwise, you will go to the left. Yeah, I agree. Yeah, so this should give you
Ma'am,
logarithm.
if for the previous question, what will be the solution for that if we have to find that a of I is equals to of I?
Yeah, so I think it will require order in time.
Terrain time.
Hmm. Because you're not able to, by looking at one value, you're not able to divide your sub problem and move there. So in the worst case, you might have to go through all of it. So I think you cannot improve on this, but I'm not sure. I'll have to look into it.
Yes.
Okay. Okay. So here is another variant of um, your local minima in array. So when you said an element is a local minimum, you looked at it, it's I minus 1 and I plus 1 at neighbor. Now let us say I change this definition, and suppose um, suppose you have to look at a neighborhood of size 2. So now I will say that I is a local minimum, or I'll call it 2 local minimum if a of I is smaller than the following 4 values: a of I minus 2, a of I minus 1, a of I plus 1, and a of I plus 2. So instead of looking at the immediate 2 neighbors, we're also looking at neighbors one that are at one more step, I mean, mm, behind or ahead. So you look at 2 cells to the left and 2 cells to the right, and this should be the minimum element. And for the sake of simplicity, assume that all the values are distinct. So okay, so how will you do this? So can you think of some modifications um, of the algorithm you saw for 1D? I mean, just finding the local minimum, the binary search thing.
And time complexity will be order n only, yeah? I think
Mm, yeah, I
that to
so
scan once.
yeah, if you scan once, it is order n. But if we modify the previous algorithm, can you do it in order log n? Mm, so let us,
Can we apply divide and conquer, man?
yeah. So what will you do? You go to the mid and then initialize this as L and R, and then check if A of mid is smaller than a of mid minus 2, a of mid minus 1, a of mid plus 1, and a of mid plus 2. So these four cells, if this is indeed smaller, then yes, we have found a local 2 minima. If not, then what are the possible cases? Sorry. So what are the possible cases? So either um, okay, let's take examples. Let us say that the mid value was 8, but this is not the local minimum. It is possible that maybe you have something smaller immediately next to it. Okay, and okay, so these are the four cases that are possible. So this was 8, and maybe this was smaller. These on the left side we don't have an issue. These are smaller, but then maybe there is this element which violates, and it could also be that this side is not an issue. You have larger number, but then this is suddenly smaller. So how will you handle these two cases? This is our mid.
We shifted to the left side only, ma'am.
uh, Left side or right side? Because if you shift to the if you shift your left pointer, that is you are shifting to this side, then you have made sure that this, so if this is your new L, then you have made sure that for this element it is at least it is a minimum with respect to the left side. So this side is guaranteed and this side is what we need to work on, right?
Yeah.
So in the previous case also what we did was we looked at the immediate two neighbors, whichever was the minimum we shifted on that side. So here also this is the minimum, so we shift on this side, right? And yeah, okay, the other two cases are symmetric. Okay, and what is remaining is maybe this is what happened. So yeah, maybe both the immediate neighbors are smaller. Then what do you do? So remember, what do we want? The invariant we want is that wherever we go, if we move to the left, we want to make sure that uh, I mean the previous two elements are larger than it. If we make a move for the right, then we want to make sure that the next two elements of the border are larger than it. So in this case, this is an appropriate choice to make. If I move my mid here, then sorry, not mid, L here, then again I'm guaranteed that there are two elements to the left of it which are larger than it. So this condition is satisfied. So no matter what the case is, you can always look at the minimum among the neighborhood. and shift to that half. So that's the same idea. So okay. So is this fine with everyone? You can check out all cases, and in each of the cases you will find an option to go. Okay. So the invariant we are maintaining is that a of L is lesser than a of L minus 1 and a of L minus 2, and a of R is larger than a of R plus 1 and a of R plus 2. So this is the invariant that we are maintaining, and if we apply similar to um, yeah, similar to what you did earlier, if you apply your induction um, step, then you will eventually end up with a two local minima, and the time complexity would still be order log n because you are having in both the step in both the cases. So is the idea fine? I have not written up this fully, but is the high level idea fine?
Actually, in the invariant, the condition will be given, ma'am.
Given as in
I mean,
like
yeah, for that, whatever the invariant in that condition only, we have to check in that range only. I think so.
yeah. So when you make when your algorithm does this left and right shifting, your it maintains this invariant that that both of these are ensured. And initially this is trivially true because initially your left is here and right is here, so there is nothing to the left of it, nothing to the right of it, so these are not even defined, so it is
Okay.
vacuously true.
Okay. Okay.
Okay, so next question that one can ask is, instead of two local minima you can define k local minima, where instead of just two neighbors you go look for k neighbors to the left and k neighbors to the right. So this element should be smaller amongst this entire neighborhood, only then you'll say it's a local minima. So then you will have more cases to deal with, and check if and the invariant you would want to show is that a of L is smaller than a of L minus 1, L minus 2 up to k L minus k plus 1, and similarly k steps here. If you can come up with such an algorithm, I'm not sure at the moment, but try this out. But at least for k equals 2 it works. At least for k equals 2 you still have an order log n algorithm for two local minima. Yeah, So more generally, can we have order log n algorithm for k local minimum? But k would show up somewhere here. It may be a multiplicative or a additive factor, but yeah, I'm assuming k is constant right now, but it will definitely show up somewhere. Okay, so okay. So are there any questions about this? I mean, about the two local minima algorithm. Okay. Okay, so try this out. I'll just talk about one more thing. And so today's session, I'll have to wind up uh, in another 10-15 minutes or so, because I have something to take care of. So um, I'll just pose one question. We will have a discussion about it. So here is here is the algorithm you saw in class. So you had n cross n grid, and you have found local minima in it. So how was that defined? In a grid, you just look at a cell, look at its 4 adjacent neighbors, and make sure that this is smaller amongst all its neighbors. So that is one definition of neighbors, but I can also define the neighbors to be, definition 2 could be that given this element, my neighbors are the diagonal entries. So this is my neighbor, this is my neighbor. Okay, these are my 4 neighbors. Or definition 3 could be, given this matrix, my neighbors are, if I'm here, then all of these, all the touching cells are my neighbors. So these are some variants that one can think of. So for this definition, you saw an order n time algorithm, right? So what was the idea? The idea was you um, sort of um, keep dividing the mid based on the columns as well as based on the rows alternatively, so that in the border that you're looking at, your minimum is guaranteed to lie inside that border, and you keep on shrinking that border by moving the column and then moving the rows. You keep on making that grid or that border smaller and smaller. That was the idea. Okay, so if I work with definition 2 or definition 3, then how much time does it take to find a local minima based on these definitions? So let us say I'm sticking to definition 3, then how much time? Log n. How would you do log n? Mm, okay, by the way, if you can find a local minima here, right, with respect to definition 3, that is also a local minima with respect to definition 1, right? So if this is minimum among all of all of these entries, then in particular it is minimum among these entries, right? So a local minima with respect to definition 3 is also a local minima with respect to definition 1, as well as it's also a local minima with respect to definition 2, because again the same logic holds. If it is smaller than all these values, then definitely it's smaller than the diagonal values. So this is the most general um, setting that you can think of, and I'm not posing this question right now, but you can think about it this way. uh, we extended this definition to two neighbors and three neighbors and so on, right? So you can also extend this definition to say that this element here, I'll call it a two local minimum if it is smaller than not only this immediate border but also the border following that. So two cells away in any direction. Okay, so okay, so that is another variant that you can think of, but we will not discuss about it right now. So how do you go about solving this exam? So if you solve it for this, you can solve it for both of these, and therefore I think we do not know of an order log n algorithm, because if we had one for this, then we would also have had one for this, but the best we know here is n. So any thoughts or any comments? I hope the question is clear. Okay, so this is the question that we are sticking to, and yeah, so okay, just to repeat, earlier what you did in class was you are given this grid, you were finding a local minima which was defined this way: find a cell such that these four neighboring cells have a larger value than this one. Now we are modifying the definition to say that I'll call it a local minimum if all these 8 cells are larger than the value. So this you know how to do in order and time. Now how do you find such kind of a minima in I mean, what is the best you can think of? Can you do order and still? Is the question making sense now? So just to be more explicit, yeah, just to be more explicit, what I mean by this is find um, I comma j such that a of I comma j is smaller than a of k comma l for all k between I minus 1 I plus 1 and l between j minus 1 j plus 1. This is the formal definition. Okay, so does the same algorithm work whatever we did here? Does the same algorithm work here as well? Okay, so why is that? So I see some answers. So Mahalakshmi says yes. So why does it work?
Because two columns are fixed, ma'am.
Columns are fixed as in. As in, like, what are the two columns that are fixed? So, um, I mean, at least in this algorithm, we were changing left and right. As I mean, as per the one discussed in class, you were constantly changing. Um, so there was this border thing that we maintained. So we always maintained a border such that there is an entry lying inside which is smaller than all these values. That was our invariant. So invariant for this algorithm was that we always maintain a border. We called it north, south, west, and east. We maintain this border such that there is an element x which is smaller than a of I for all I in north, west, east, south. So you look at every entry here, this value is going to be smaller than all of these. That was our invariant, right? So right, so in that invariant we always kept on shrinking this border until eventually you only are left with a one by one grid and all its neighbors are larger than that. So my point is that when you actually end up in that case, you are smaller than all of these, right? The border also contains these elements. Okay, so this same algorithm will actually work for as it is for this definition as well, and hence for this definition as well. It's just a matter of analysis. It's just the observation that the border will actually contain these elements as well. So I think the n log n one, as it is, does not give you a solution for this. Um, yeah, okay, but the border thing is actually stronger and will give you an order and time algorithm for stronger definition as well. So um yeah, so I mean, we cannot, due to time restrictions, we cannot get into the details of this because the actual lecture itself was, I think, more than an hour, for more than an hour. So we'll not get into this algorithm, but just go to that step and check out for yourself that this will work for a stronger definition itself. um okay, so are there any questions about anything we discussed today?
No, ma'am. Thank you very much.
Okay, thank you. So next we will meet um, upcoming Tuesday, which is 18th, I think. Same time.
Sure, ma'am.
Okay.
Excuse me,
Thank you.
ma'am. Uh,
Yes, yes.
Ma'am, in that question which I asked from you, like A of I is equals to I think, ma'am, binary search is applicable for that, and this was the most efficient one. Because if a of mid is equals to mid, so then so the that is we are able then we are
Yeah,
able to
that
find the
case
mid.
is fine. Yeah.
And if a of 2 is equals to 2, so that means ki at the 2th index we get the value 2, and which was the condition. So we can solve it like that, isn't?
But it could also be that okay, where is that? Yeah, this one, right? So it could also be that you went to the mid. At this point it did not match. Okay, so because duplicates are allowed, my array could be like this, right? um, so you don't have any element, sorry, whatever indexing is there. Okay, I'll just, yeah, so on this side you don't have anything where
Ma'am, there is no duplication. It's a unique, distinct, indistinct elements are there, no?
but
So,
okay, I thought you said with duplicate, so that was like
nahi,
the
nahi, nahi,
entire discussion was
indistinct elements.
okay. So mm okay, but okay, such an entry is not even guaranteed, right? So um, I mean, so how do you decide whether to go to the left or to go to the right? What is the algorithm?
Ma'am, it was like
Yeah, if you are in this case, then where do you go?
if a of mid is equals to mid, so that means we are found if the values are equal. And if a of mid is greater than mid, so we go to the left. And if a of mid is less than the mid, then we go to the right side.
Okay. Mm. So in this case, you are saying you will go to the left. Is that what you're saying?
Yeah, yes,
Yeah.
ma'am.
So
If a of mid is greater than mid, then we move left.
yeah. So now what could happen is my array is array is like this, 4 3 2. Okay, so if you go to the left, you will not find your correct answer, right? But maybe,
Ma'am, hello, ma'am.
yeah, yeah.
Yeah, or else if A of mid is greater than that of mid, then that time the element can be stored at sorted order, ma'am.
The array is already sorted. The given array is already sorted.
If I'm actually asking that if the array is not sorted in order,
Mm-hmm.
then that time if A of mid is greater than that of mid value, then that time that values can be stored at unsorted values, right, ma'am?
Yeah, but in that case, you cannot do better than in any way. So you will have
Okay.
to, yeah. Okay.
Okay, ma'am. Ma'am, and one more thing, what is the time complexity for this, ma'am? If the array is unsorted array, then the time complexity will be changed, right, ma'am?
Um,
Unsorted array on
okay,
that
so
array.
your array is unsorted. They are all distinct. You want to find an element where a of I is equal to I.
Okay, okay, fine.
No,
Thank you,
I'm
ma'am.
I'm confirming your question. So for that's your question, right? Then you need order n or omega n, theta n. That's it.
Some time complexity for this is order of log n.
Yeah, yeah. Let me uh, clear things in the stack. So let me just address that previous question. So for the question that she is asking, you have an unsorted array, right? So there I'm saying you cannot do better than n.
Yes, ma'am. Yes.
Okay. So coming back to your question, so this part of the array should be discarded because if a of mid itself is larger than mid, then it has to be the case that for all j greater than mid, this inequality will hold. So you will not find, yeah, so you will not find this a of I is equal to I there. But what I thought you said initially was that there are duplicates, in which case you can come up with a counter example. You'll have to go
And
through.
ma'am, the time complexity is order of n, na? Order of log n.
Yeah, if there
Yes,
are,
yes.
yeah, if it is this
No
way,
repeat.
yeah.
So this we can solve this question by using the binary search, isn't it?
Yeah, if it is
Thank you,
this
ma'am.
way. Okay,
Thank you very much, ma'am.
okay. Thank you all. So, uh, yeah, just one more note. It is possible that it's very likely that we might have to shorten the next tutorial as well by 15 minutes or so. Just letting you know. So, similar to today, we'll try to end around 8:45, but next time on, we'll have full 2 hour tutorials. Okay. Yeah. Okay. Thank you all. See you next time, and I'll upload these recordings by today. Okay.
Thank you, ma'am.
Bye.
Thank you, ma'am. Bye,
Thank you.
ma'am.
Bye.
Thank you, ma'am.